Well, welcome to today's lecture. We'll continue on what we started last day on gyroscopic effect. So last day you saw me, it's not me, it's a picture of another person, but you saw the demo when I rotate a wheel, let's say like that, spinning the wheel about its axis. Right, the center axis. And while it's spinning, so let me do a better job. So about this axis, the whole thing is spinning, right? And then if this person rotate the whole wheel, right? And maybe, let's say, lifting his shoulder, do something like this. So which is an axis coming out of your screen, or sorry, going into your screen, use your right hand, right? But anyway, it's about an axis normal to your screen. Then we saw a magic moment will happen, a magic torque. I keep saying moment. You know, probably you've heard this joke that a student asks a teacher, what is a torque? And he says, just a moment. So I hope you got the joke. So anyway, torque and moment, they are the same. So if we have these two, a moment or a torque cause this person to rotate, okay? And that moment, which we show it by M, it has the unit Newton meter. It's a torque, it's a moment. If we have the speed of this wheel rotating with omega, so this is then the speed of the wheel, right? Spinning, and he moves his shoulder with the speed omega, we show it with capital omega, big omega, then just to distinguish it, this moment is I, which is I of this wheel, so this I is about this axis, because remember I, unlike mass, has to be about an axis. And then omega cross omega. And this is cross product. And we have a minus sign here. If you saw in a textbook a formula like this with no minus sign, that's also correct. It's just people switch the position of these two. But we will stick with the formula that is common in most of the textbook. And you need to be careful which one is rotating which one, right? This red small omega is not rotating the shoulder of this person. The shoulder of this person, like this blue omega, capital omega, is rotating the whole axis of this red omega. And where this magic torque coming from? So we said we don't go through the math, but it has something to do with conservation of angular momentum. If you are interested, maybe in one of office hour, I can go through the math, but it's just the math, and on internet you can find. In this course, we just look for the application, which is this basically formula. So I showed you a demo, and this is another one. If I can play it, hopefully with your internet speed should be fine.
I'll lift my feet off the ground. Try not spinning. My assistant's going to come and spin this for me. So I have some angular momentum. Now when I rotate it, start to spin. If I want to stop myself, stop. If I go the other way, I spin back around.
So probably the speed is not fast, and even the demo that I showed you, I didn't spin fast. The reason is being like this omega is small, like when he lift his shoulder to rotate it, right? If you do it faster, of course, it's gonna spin faster. And moving the whole mass of this person requires a lot of like a big M to rotate it. And the whole things will start rotating with speed N. Okay. So this is what we showed you. So it has a lot of application. You saw in the video for the bicycle. So it is then responsible for your bicycle staying up. You can think of this wheel, let's say the front wheel, as the main wheel that this person is rotating. If this wheel wants to, let's say, tilt to the left or right, there's going to be a moment to keep it balanced. Your future helicopter, your personal helicopter also relies on gyroscope for precision maneuver. This device here on the right is one of the devices that UBC team, which I'm supervising, they are building right now for their capstone. Probably when we return back to in person, you are welcome, let me know, to come and see it. The lower half of it has been built up to this green frame, but the rest stopped because of COVID. So what we have here is this person is sitting on this platform, and this person can rotate about this vertical axis. All right, so it can rotate about this vertical axis. Think of it as omega. And also the whole frame here can rotate about this blue axis, like something like that. Think of it as omega. Okay, so the person spin about its center, about the vertical axis, and then the whole things can lift up and start rotating. This is a research in kinesiology department. They want to know things that happen with the balance of a person, and also do some tests in amusement park with all these crazy machine, not roller coaster, but other machines, what will happen to a person's health. Anyway, so this team has to also design all the bearing and stuff for this mechanism and for this machine. And the whole shaft here is staying on it. It's hard to show it here, but it's a bearing here. Let's call it bearing A, and another bearing here, bearing B. If we are not aware of the gyroscopic moment, we may just be simply consider the weight of this person, the weight of the frame, and do the math and find out the action on A and B and design the bearing, which is something that you will learn next year in, I believe, MEC 325. Yes, MEC 325 design course. You will learn how to design bearings. Before that, you need to know how to calculate the forces. And this is something that you were supposed to learn in statics or in MEC 260. When you have a shaft, let's say a beam here, and you have the weight and everything, and you calculate the forces A and B. But the external loads here is not just the weight of this person and the weight of the frame, it's also another moment or torque coming from these two omegas, okay? You don't need to confuse yourself for getting into that, but you can think of the omega, the moment that creates is going to be perpendicular to these two axes, okay? The gyroscopic moment is always perpendicular or 90 degrees to these two omega. All right. So what is this? Can I get rid of this guy? Oh, by mistake, I pressed something here. Okay. So believe it or not, each of you guys in each of your ear, left or right, you have a gyroscope, and it is responsible for your balance. For some people, unfortunately, it doesn't work properly. So the gyroscope, you can think of it's in these channels somewhere in the ear. I don't know the terminology, but people call it inner ear balance. And for some people, unfortunately, it doesn't work properly, or because of an accident, or maybe when they were born, so they have all this vertigo, they cannot balance when they walk. And luckily, due to this gyroscope, people could build a tiny, tiny gyroscope. You can think of 3 spinning discs, and they put it inside the person's ear, and then the person normally can be balanced. So when we walk or we do maneuver, so our eyes seeing around, our legs and the body feel around. So we use all these sensors, our brain use all these sensors to balance. And whenever this information is not enough, then our brain relies on this gyroscope, the natural gyroscope. So we should be all grateful that our gyroscope is working properly. You can read from this link that I put it there for you. And it's a good device for exercise. Like this one, you can buy it from Amazon. There is a wheel inside. I got one, maybe I can show you. Let me switch my camera. Okay, you guys can see my screen, my hands, my fancy game mouse. Let me get rid of that. So if you can see it, my screen, this is, okay, that's way. That spinning gyroscope, if you just on Amazon Google gyroscope, you will see that one. NSD spinning, what it says, 1 minute exercise and powerful. So what it has inside it, there is a wheel. You can see it's rotating, right? These green things, right? It's rotating. Okay, so this whole, and then it can rotate about this axis. And also the whole things can rotate. It's hard for me to rotate it. Can rotate about this normal axis. Okay? The whole things can rotate. So you'll see if I move it, it can rotate. Okay, it's hard for me to show it. Now, imagine if this thing is rotating and I'm holding it in my hand, and with my hand create another rotation, then there will be a gyroscopic moment and create a lot of force inside it. So it's good for exercising my, let's say, hand and the muscle around here. Let me show you. Again, one of those things that I wish we were in person so you could feel it, but now you can just trust me. So we use this band here just to spin these things. So I move it around that for the initial spinning. And the first time I tried it, I didn't know the force is so big. So if you're not careful, then the whole thing is going to fly off and hurt people. Or you can have fun with somebody, and while it's spinning, give it to somebody, and it's difficult for them to hold it. So if I hold it like that, and if I pull the whole things, and now inside is the spinning, and if I move my hand with an omega, it creates a very, very large force, which right now it's even very difficult for me to hold everything. I'm not sure if the video you can see, but it's right now, it's very difficult to hold it, and it's very good for the exercise to do like that. Okay. So that's about this toy. And if you guys are working with mouse a lot, I suggest getting one because it can be really good for your Tundle, right? Because probably you're spending a lot of time with computer. And maybe like me, doing a lot of gaming. Maybe later I'll talk to you about the games that I play, and we can go on a match. So let me check to see if there is any question in the chat. So nothing in the chat. Okay. And then if you recall, I showed you this toy that I have in the very first lecture. So this device, it has this blue stand, and then the top part, which is like this blue section, is just sit on top of it. So obviously we know because of the heavy mass of these things, which is going to be somewhere in the center, let's call it mg, it will fall off, right? Because it creates a moment and it falls off. But you guys saw when these things start spinning, the inside, which is again difficult to show it. Yeah, if it starts rotating, it is this guy inside. And then the whole thing wants to fall off, but because of gyroscopic moment, there will be a moment that lift everything up and hold everything in place. Let's call it M. Of course, this is 3D. It's difficult to show it now. And also, the entire system starts rotating or spinning with a speed n. Or you can think of it this way. You have n and you have omega. You have n and you have omega in this scenario. But this n initially come from, let's say, an initial force which start rotating, like initial, let's say, pulse that we apply. And because there is not too much friction in the system, it start spinning, like create this capital N. We have N and we have omega. As a result, the whole system stay in a certain angle. And we'll solve one example, so you will see how we can calculate this angle. Let's call it for now theta. Okay, and this mechanism or any gyroscope is called a precision gyroscope because it's a device either you can use to measure this angle, or depends on this angle you can measure your speed, because you know there is a relation between these parameters. For example, in this scenario, simply we can write that the relation here, if I have omega and n, then I n cross omega, which creates a moment, it should balance like the moment that created by this mg, which will be mg multiplied by a distance, which this distance, let's call it for now d, but later carefully we calculate it. If I show the side view of this device, let's say side view, what we have here is the mg, the weight of the entire things, which let's assume that the weight is a center of gravity somewhere there. Okay, and this is that black axis that we had. All right, and this is this. You can think of that pink one. All right, so what is d here then? D is the distance if we want to calculate the moment for this mg here, d. If I call this angle theta, then you know d will be equal to what? It's, let's say you have this distance, let's call it r sine theta. So you will see this like capital N, omega, m, and theta, they are all related. So roughly you get an idea that people can use this device for either estimating this angle, or if they know the angle, they can use it for rotation. To find out one of these speed, either n or omega. Let me show you again my toy that I showed you in the very first lecture. So this one you saw the mouse moving that way, and these things. So this is a device, right? It can spin about this axis. And by the way, you can buy it on Amazon. If you're interested, let me know. But there is also a cheaper version available. This one comes with a motor that you can spin it, like this simple motor. If I want to get the speed to a higher speed, I just attach this one over here, so and the whole things can rotate. Like I can spin this one fast. It goes up to very high speed, like 3,000 RPM, or maybe more, 12,000 RPM. Okay, this is the stand. And these two, as you can see, they are not connected. And this thing is on not a bearing, but with no friction, it can rotate. The whole thing's being 3D printed, right? Simple. And this one, of course, being machined. Even you can build one for yourself. So obviously, if I put these things here, it's not going to stay. It's going to fall off, right? But let's spin this one. So I connect that guys over here. Okay, turn it on. Now it's spinning. Even it's now difficult for me to hold it in my hand. And if I slightly want to rotate my hand, it's just gonna fall off. So a little unsafe, which sort of explained what we saw in the previous toy. If I put it over here, so it stays in a certain angle. Even if I try to move the whole things, my table, shake it, it's going to be stable. And if I try to apply load here, like even if I put a big weight here, it go and stay on a certain angle. All right, and it's going to keep moving for the rest of our lecture. Let me check to see if there is any questions. What happened to the negative sign? Oh, okay. I forgot the negative sign. Yes, there is the negative sign. I just want to show you the magnitude if they are balanced. Let's move back to our lectures. And let me stop this guy. So that guy stopped. That's over there. All right, yes, we have the negative sign as well, but over here, I just want to show you the magnitude. like whatever the magnitude of this guy is, it has to be equal roughly to the magnitude of this guy. We'll solve one example later, not today, but later. So you will see how it works in numbers. Let's just solve one example together to make sure that you understand this topic. And here is the example. You don't need to think complicated. Whenever you have two omegas, one of them is rotating the other one. There's going to be this magic torque or magic force you can think of that creates a torque and try to move or spin the whole structure in a direction which is 90 degrees to those two omegas. Okay, it's perpendicular to the plane of, let's say, those two omegas. Here I let you guys to read this example. This is a question from last year final exam, and try to see if you can solve it. So you have about 2 minutes or 3 minutes, to be fair, to read it and try to understand it and roughly try to guess something. And probably I will ask a volunteer to tell me what's going on here and how should we approach solving this problem. Like always, first try to figure out the mechanism. What is rotating about what, or try to visualize the whole things. So I hope you guys are still thinking about it. While I'm trying to create a 2D image of that. And we had this guy. So this is the side view of that things, approximately. So like this distance, and let's say this distance. What else we need to know? The whole things. Okay, this is a side view. And this is B. And this is L. This is the weight of this guy, which is how much it is? So the blade have a mass of M. Okay. mg. And what is the mass of the other one? Like this guy. It says it is m/4. So this is our diagram. You can think of free body diagram. And O, of course, it's just a pin. So apply OX and OY. Or OZ following this direction here, and OY. It's just a pin, right? Okay. Now, a volunteer, if you guys can tell me what's going on here. So if, like we have the whole setup, this side view that I draw here, right? And it says that everything is balanced when the fan is off, I guess, right? And then when the fan starts rotating, probably everything is going to fall off. We want to find this distance B so that the whole thing stays horizontal. A volunteer, if you guys, one of you can tell me how we can approach solving this problem. Just tell me what should we do. Any idea? I can draw the same things also here. So this is the weight of this fan, mg. This is the weight of this block, m/4 g, right? So, nobody?
Balance the moments.
Balance of moment, that's true. Balance of moment here, like on this image that I draw here.
From the side view image. Yeah.
Okay, so that's correct. Balance of moment here. So we know if these things we want to stay horizontal, then we know simply m/4g multiplied by b, right? Try to rotate everything counterclockwise. Has to balance the other one, which is mg multiplied by L. This is a static, right? This is a static. If everything is not rotating, then simply you will find out B from this equation. So this is a static. And you say, okay, B, the distance has to be, get rid of mg, it has to be 4L, right? Yes. But what about when we are in dynamics, when things are spinning? Still, these things is there. It doesn't go away. But also we know that there is some extra things happening here because we have 2 omega, and whenever we have 2 omega, we have to open our eyes and say, okay, wait a minute. If I have 2 omega, this small omega is being rotated by this large omega, then something must be going on here. And that must be a moment. Let's find out the direction. So that moment, if you just follow the formula, m is equal to minus I omega cross omega, or you can just use your right hand rules. Let me turn off my cell phone. Okay, done. Your right hand rules both give you the same answer. So what is omega? It is minus, tell me, k, right? Something k. So, or if you want to show it like the notation, so sorry, it is j because it is in y and it is minus coming down. And what about omega? It is omega k and it is positive, right? Look at the direction of z and y. So let's put everything there. It will be minus I. So I have another minus there. So omega j cross omega k. So ijk j multiplied by k give me I, right? So it is then I omega omega I positive. Am I right? Please correct me if I'm wrong. So it's going to be a moment like this direction, or if I want to show it over here, it's going to be a moment in this direction. And so it's helping like this m4 over g. So I need to add it here then, because you just here we just write down the values. It's going to be I omega omega. Okay, so this is our main formula. If you guys are agree, or let's say if you're not agree, let me know and see what is missing here. This is the main relation. And it's important, instead of just following the formula, just have a feeling for it, what's happening here. And hope the direction and everything is correct. And if that's correct, this is what balanced the whole things. What is I here? So the question gave me the radius of gyration, k, about z. So over here, I can quickly calculate, because we know k is equal I over m. That's the formula that we learned. It's about z-axis, so I can find Iz simply, which is k to m. Let's substitute it here. So it's going to be m k squared omega omega plus m over 4 gb is equal to mgl. Get rid of m, and from here I can find b. So b will be equal to so we divide everything by m, right? And maybe mg. So b's will be equal to L minus b over 4. Am I right? No. Okay. Get everything's there. So it's going to be minus sign there. And it will be k squared omega omega divided by g, and then divided by 4 or multiply by 4. So let me write it down the whole thing. So it will be then 4 times L minus K squared omega omega G. And this is the distance that we can use to adjust this distance, like B, because this mass M, we can move it and adjust everything. Because we know L, we know K, the radius of gyration, question gave it to us. We know the speed of our fan is rotating and the big omega that we want the whole fan rotating, and we know gravity. So let's test this formula. If we turn off this fan, it means omega will be 0, right? Small omega will be 0. Put omega equal to 0. What the value will get for B? 4L, what we had previously for a static. All right, the faster this omega is rotating, the fan is rotating, then you need a smaller B, right? You can see it from this formula. What if the person who is rotating this thing decide to change the direction of this big omega? If you change the direction of this omega, it means the faster you're rotating it, then you need a larger B. Because if you switch the direction of this omega, then the direction of this moment will change, right? Then this green M, this green torque, instead of helping this balancer mass, it's going to be in the opposite direction. I hope with this example, you guys understand the gyroscopic moment, at least the math, how you can apply it to solve a problem. If you don't worry, I'm going to still solve more examples, like variety of examples in different applications, so you will see it exactly what's happening. But this one is a good one because it gives a feeling, because you can visualize the fan and the direction of like rotation and everything else. And clearly you will see this M that is a vector, like this green M, which is a vector here, right, is on x-axis, so it is perpendicular to the direction of two other omegas. Like we have omega, which is in z direction, and we have this big omega, which is in y direction. So you will see this M is perpendicular, and this cross product also confirmed that. Oops. Any question, guys, here? Are we good? And please solve some problems and practice. I guess in problem set 6, I put some examples for you. Let me save this note. And if we have 3 or 4 minutes, I'm just gonna briefly tell you what we will do next day. And hopefully you can do maybe a quick review of at least these slides or the textbook. So be ready for that. Next day, we're going to talk about the energy, kinetic energy and potential energy, but for rigid bodies. So you guys remember when we were in topic of particles, if we have a mass m, like a particle, and this mass m, let's say, is moving on a straight line or maybe on a curve, doesn't matter. Whatever motion it has. Let's say general path of motion. And maybe there are some forces acting on this mass. Let's say a force here and maybe another force there. Maybe the weight. So F, another F. So we said, let's say this mass going from this position 1 to a new position, let's say 2, we say the energy and the work, they should be balanced. So in other words, whatever energy it has here, over here, plus the amount of work to get this guy from 1 to 2 will be equal to energy at point 2. Okay, this is the conservation of work and energy, which we discussed that one, and hopefully you know how to apply. Then we said this E in general has 3 elements. It has kinetic energy, which we show it by T. It has potential gravity energy, which we show it by U. And it has potential elastic energy, which in order not to get confused with velocity, we add an E to show it its elastic energy. So this is kinetic energy. This is potential gravity. And this is elastic energy. Right? This is what we had before. And quickly, we know T is equal to mv squared. U, you saw it is either positive or negative, depends on the reference we select. It is mgh. And VE, you saw it can be either half of k x squared, or if it's a torsional, I will write it down here, VE was half of kt theta squared, right? If it's a torsional spring. Do you remember this? So this was the foundation for the conservation of energy. So when we get to rigid body, everything stayed the same, like the potential energy, the elastic energy, the formula, they are all the same, except for potential energy, instead of, because now you have a rigid body, okay? You don't have like a mass. You assume that the whole mass is at the center of gravity. So I'm gonna write it down, or let me write it down here. We'll be done in 30 seconds. For a rigid body, assume the whole mass is at its center of gravity. Like G, point G, all right? Then you will use simply this formula, mgh. So its center of gravity moves from this point to another point. The position is changing, so you have like the U. Everything stays the same. If you have a spring, linear spring, or a torsional spring, that's also stays the same, okay? The only things that will change is this guy, T, kinetic energy. It's not simply be 1/2 mv squared, because now we have something else. We have I, and I is mass moment of inertia, and mass moment of inertia creates some energy, and this is what we were going to discuss and find the formula next day. And you will see it's super, super simple and very useful, unlike particles, which it doesn't really have so much application in real life. Rigid body has real application, and you will see how you can use the kinetic energy and conservation of energy for a real mechanism and real application. So I will start by this page next day, knowing that you know those background information. And if you forget, please go back and review the topic of energy that we had before for particles. And then I will solve one simple example here, a little bit complicated example here, and a fun example, example 3 here. But please take a look at these 3 examples and be ready for Friday. I will also solve the problem that left from last day, not last day, from the lecture before last, which we solved it halfway through. Most of you guys solve it, but then some of you ask question to check if your solution is correct. So what I will do, I will solve it. Then you can compare with my solution, and you will be ready for the quiz 8 this weekend. All right. So with that note, this is the end of lecture today, but I can stay for another 5 minutes in the room. If you guys have any question, feel free to ask. And I'm going to check the chat to make sure that I haven't missed any question there. Nothing there.
Sorry, could you go back to the final exam question?
This here?
From the last year.
Okay, the last lecture, right?
No, from this lecture,
Okay, over here?
No, I think it was in the previous slide.
All right, so in the gyroscope one.
Yes, the gyroscope one, sorry.
Okay, this is what you meant. Okay,
yes.
Go ahead, please.
Sorry, I'm just trying to understand. So how come we put the moment equation that we found, the I capital omega and small omega, on the left-hand side and not like the right-hand side?
That's a good question. So first of all, forget about this whole mechanism. Let's figure out the direction of this M. Do you agree with this direction or no, that I draw on this image on the left?
Yes, yes.
Okay. So if you agree with that, it is trying to rotate the whole things clockwise or counterclockwise. If you look at the side view, now look at the image on the right, like this green M that I draw here.
I guess it would try to rotate counterclockwise.
Counterclockwise, exactly. And this balancer mass, it also try to rotate everything's, do you agree? Counterclockwise, right?
Oh, I see. Okay.
So these two agree, and then this red mg, the whole weight of the fan is against them. Okay, this is how we write it. Or instead of using this, you could just use the plus and minus, follow plus and minus. But I found it's easier and more intuitive to understand what's going on. Now, do you understand what's going on and the direction?
Yes, I see. I understand it better now.
Okay, awesome. So Eric, this question, is it easy for you or you follow every step?
I follow the steps, but I'm just trying to understand how like all the torque works, all the moments, all of the forces work.
Okay, but that's good that in overall you see what's going on, right? Here we have a fan is rotating with omega, and then we are spinning the whole things with this capital omega because we want like it cool the entire room for us, right? So, and since we have these two omega, we have this M. This is one M that we know it exists, whether we want it or not. And this balance mass M/4 and the fan mass also, they are there. Okay, we cannot do anything about them. And all of them has to be balanced. Why? Because the question asks us that finding this B so the whole thing stay horizontal, not moving.
Okay. Right? My other question was, you earlier talked about how if the fan blade rotated the other way,
right?
What would be the effects of it?
Okay.
Or like, how would you try to negate it?
So look at this formula that we had here. Like it has a concept here. It says minus I omega plus omega, and we follow this step and we figure this green M that I draw here, it is in this direction, right? Now, if you change one of these omega, its direction, either maybe direction of the fan or maybe the direction of rotation. One of these ijk will change, and then the direction of this M will change as well, right? Do you agree?
Yes.
Okay. If the direction of this M is changing now go back to this image, the side view on the right, if the direction is changed, instead of being clockwise, counterclockwise, imagine it is clockwise now. Then this green one that I put it on the left side equation, now I have to put it on the other side of equation.
So would B just, do we just have to increase B?
So you just follow this, solve this one on paper for yourself, for me now, okay? So you have this one on the side here, right? Like this image that we have on the right. So imagine that we change just the direction of this omega, this small omega, instead of going that way, it's spin the opposite way. If it is spin the opposite way, it means the direction of this M will change. Instead of moving that way, now let me use the pink color. Instead of going that way, it will now go this way. Okay, this pink one, the opposite. This will be our M. And why it changed? Because the direction of one of these omegas changed. So now let's look at this one. This red MG try to rotate everything clockwise. This pink one also is try to rotate everything clockwise. So MG has to balance both of them.
I see. Okay.
And this sign here that we have here, instead of this one being negative, it will be positive. Why? Because this I omega multiplied by omega moves to the other side of equation, right? This guy will be over here.
I see. Yeah, okay.
Okay, and then you will see now you need a very large B to balance everything. Okay, so to avoid that, if we decide to change for some reason, if we decide to change the direction of omega, this small omega, to conserve everything as it was before, we can also change the direction of these omega as well, these two omega. If we change the direction of both, so negative multiplied by negative gives us positive, so everything will stay the same. Okay?
Okay.
So I suggest try to solve the same example, but work with the different direction. For example, for yourself, change the direction of this omega, capital omega, change the direction of the small omega, and so on, and see how things working out. Okay?
Okay.
The formula stay the same, it's just this plus and minus.
Okay, thank you.
All right, is it clear now?
Yes.
Awesome. Any other question?
None for now, but I'll email you if I do have any more.
Awesome. Good. Have a good day.
Okay,
See you
thank
later.
you.
Goodbye, everybody.